Hello everyone and welcome to our presentation on our work real-time non-invasive imaging and detection of spreading depolarizations through EEG, an ultralight explainable deep learning approach. So I'm Professor Martyn Boutelle of the Department of Bioengineering in Imperial College, and I'm presenting this work along with my PhD student Yinzhe Wu and my colleague Dr. Guang Yang and his team. This work comes from a long-term collaboration with Dr. Sharon, Jewell and Professor Anthony Strong from the Department of Basic and Clinical Neuroscience, King's College London. We're excited to share our findings with you today, which we believe represents a significant advancement in the field of neurocritical care.
In neurocritical care, a core objective is to prevent secondary brain injury, a major driver of poor outcome in patients with acute brain injury. A key factor in secondary brain injury is spreading depolarization, or SD, often described as brain tsunami. This phenomenon was first observed by Leo in 1944 and is a critical independent cause of secondary brain injury, affecting patients with traumatic brain injury or TBI, brain hemorrhage, and millions of stroke patients worldwide. Prompt detection of spreading depolarizations can significantly enhance treatment timing and improve patient outcomes. Spreading depolarization is a pathophysiological wave of massive depolarization that spreads across neurons in the cerebral gray matter. Originating from the initial focal lesion, it is characterized by a sudden and sustained breakdown of neural transmembrane ion gradients. This breakdown is highly disruptive to normal brain function and is a significant contributor to the progression of brain injuries. Here, we illustrate the rate of change in reflectance captured in time-lapse video of intrinsic optical signal, or IOS, changes on a human cortex during a spreading depolarization, demonstrating the destructive nature of these waves. Currently, the clinical gold standard for detecting spreading depolarization is invasive electrocorticography, or EEG. However, the preliminary studies suggest that EEG, which is non-invasive, could also be useful for detecting these events, particularly benefiting millions of inoperable stroke patients. While EEG provides clear observations in both direct current, or DC, and alternating current, or AC, segments, EEG faces challenges due to noise in AC segments and the loss of key features in the DC segments.
The main objective of our study was to address the critical need for a non-invasive method to detect spreading depolarizations, or SDs, in real time using electroencephalography, or EEG. SDs are a significant cause of secondary brain injury, and current methods for detecting them are invasive and time-consuming. Our goal was to develop a lightweight deep learning model that could accurately detect SDs using EEG data, even with low-density electrode setups, and process this data rapidly enough for real-time clinical use.
In our methodology, we focus on enhancing the detection of spreading depolarizations by introducing a novel approach that combines traditional EEG power data with a new imaging biomarker, the spectrogram. This fusion is critical because it allows us to capture more complex patterns in EEG data that are often missed when using the power data alone. A spectrogram is a visual representation of the spectrum of frequencies in a signal as it varies with time. By transforming the EEG time series data into spectrograms, we are able to observe and analyze the frequency domain more effectively. This is particularly important for detecting SDs, which are characterized by specific changes in both time and frequency domains. This method leverages the strengths of both 1D time series analysis and 2D image analysis, creating a more robust detection framework. It is this dual approach that allows us to improve detection accuracy while maintaining the model's lightweight nature, which is crucial for real-time processing in a clinical environment. Additionally, we incorporate a confidence score into our model. This score quantifies the likelihood that a detected event is truly an SD.
The main contribution that AI made is not just making predictions. It is about how to assist the doctors to making intelligent decisions. Instead of giving mere prediction results based on input data, this method highlights the confidence score and allow the doctor to explain the results to understand how the AI made the decision based on the input data.
To implement this approach, we developed a specialized network architecture designed to handle both spectrogram and EEG power vectors simultaneously. The architecture consists of two main pathways. The first pathway is the spectrogram pathway. This pathway processes the 2D spectrogram images using a series of convolutional neural network, or CNN layers, for automatically detect spatial hierarchies in images.
Most important of CNN-based method is like we can make it more generalizable. For example, some of these traditional methods, they may just working on limited data sets, but the CNN can work on many different data collected at different centers using different data collection protocols.
In our case, the CNN layers extract the key frequency domain features from the spectrogram that are indicative of spreading depolarizations. The second pathway is the power vector pathway. Parallel to the spectrogram pathway, we have a 1D CNN that processes the EEG power vectors. These vectors represent the traditional power data from the EEG, capturing the amplitude variations over time. The outputs from these two pathways are then merged in the network's later stages. This fusion step is critical because it combines the detailed frequency information from the spectrograms with the temporal information from the power vectors, creating a more comprehensive feature set that improves the model's detection capability. To ensure that our model is not only accurate, but also practical for real-time use without the need for a GPU, we focused on keeping the network lightweight. We optimized the model by carefully selecting the model's parameters and limiting the complexity of the architecture, ensuring that it can process data in real time, specifically under 0.3 seconds per hour of EEG data, practically viable for deployment in clinical settings where time and computational resources are often limited. Moving on to the results, our model demonstrated high detection accuracy overall. By fusing both spectrogram and EEG power data, we achieved a higher detection accuracy. This fusion also resulted in fewer false positives, thereby increasing the specificity of our model. As we further analyze our model's performance, for patients with no SD, we observed that the fusion of spectrogram and EEG power data significantly outperform other methods in ruling out SD as well. Additionally, as demonstrated in this figure, incorporating a confidence score enhances the explainability and trustworthiness of our detection outcomes. This is essential for clinical applications as it fosters acceptance within the clinical community by ensuring both reliability and comprehensibility, paving the way for broader clinical use.
One of the key innovations of our work is the dramatic reduction in processing time. Previous methods can take up to 2 hours to process 1 hour of EEG data, which is not practical in a clinical setting. Our model, on the other hand, processes the same amount of data in under 0.3 seconds, making real-time monitoring and decision-making possible. This advancement has the potential to significantly improve patient outcomes by enabling earlier detection and treatment of SDs.
In conclusion, we have developed a novel approach for the non-invasive real-time detection of spreading depolarizations using EEG and deep learning. Our method achieves high specificity and sensitivity, while also dramatically reducing processing time to less than 0.3 seconds per hour of EEG data in CPU.
I think that's one of the most important features because if we think about the translational study, normally at the clinical settings, we wouldn't have really heavy or powerful high-performance computing on the sites. So that's the reason we want to compress our model to the smaller sizes, and also we can make sure that can be run on normal PC, and then let's can maximize the potential of the deep learning.
Looking ahead, we aim to refine our model by incorporating data from a broader range of patients and conditions. Additionally, we hope to collaborate with other clinical centres to further validate and potentially standardise this method across different healthcare settings. Despite these limitations, we believe our work lays the groundwork for significant advancements in non-invasive brain monitoring. Before we end, we'd like to acknowledge the support of our funding bodies. These are UKRI, an MRC Clinical Research Training Fellowship for Sharon, a UKRI Future Leadership Fellowship for Guang, and we'd like to thank collaborators who made this research possible. Thank you for your attention.